It's time to spend a little more time talking about references, copies, and deep copies. And you need to get all the way through this video because the concepts may seem obvious at first and maybe a little repetitive, but you're going to see some very important nuances as we get to the end. Our first basic step is to understand that there's a difference between an object in memory and the name that refers to that object. So we may have several cats. I know, they're beautiful. That one looks a little mean. Now these cats exist at some memory location, but we can't access them unless they have a name. So let's call this one Sam, and this one Puff, and this one Fido. But the name of the cat and the cat itself are not the same thing. We may sometimes call this cat Sammy. Both of those names point to the same cat. We can access the cat in either way. It still won't come when you call it. We might even completely change a cat's name, so that instead of Fido, we decide we're going to call this cat Fred. The name Fido no longer exists, but the cat hasn't gone away. He just has a different name. We can reassign the name of a cat from one cat to another, so that Puff now refers to the first cat instead of the second cat. Now in reality, we have to be careful in Python because once an object loses all of its names, Python comes along and removes the object. We call it garbage collection. But we won't let that happen to these cats. Let's refer to these cats as cat 1, cat 2, and cat 3. We need to go a little bit deeper and talk about immutable collection like a list. A list is an object in memory, but it's pretty simple. It only contains references to other objects. A list without a name connected to it won't continue to exist. Just like any other object, it would be garbage collected. So let's make sure to give this list a name. We'll call it cats. And we realize that if we make a statement like cats 0 equals cat 1, that what we're really doing is just adding a reference in this list to this object that already exists. We can do the same thing with cat 2. So we have cats pointing to this list, and the list points to objects in memory. We can add another name to this list. We might say something like felines equals cats. This is, of course, called an assignment. What it really means is, whatever object cats was pointing to, I want felines to point to the same object. So I haven't really changed anything. I've just created another name for this object. I can now call it cats, or I can call it felines. This is important. I have two references to the same object. They're not two different objects. So that if I now say cats 1 equals cat 3, in other words, I'm taking this reference to cat 2, and I'm changing it to cat 3, then I've not only affected cats, I've affected felines as well. Both of these names point to the same list object, so changing one changes the other. If we really wanted to create another list object that we could change without affecting the first one, we'd need to use one of the methods of copying a list. Let's start over. I've pushed this aside a little to give us a little more room. Now there are a number of ways that I can copy this list rather than just pointing another name at it. For instance, I can say felines equals cats. So far that's an assignment, but if I add an empty slice on the end, the slice actually creates a new object. So it's a trick. We get a new list, and it's set up exactly like the old one, with the same references, but it's a different object. So that if we now say felines 1 equals cat 3, we're going to move this reference in position 1 of felines to cat 3, but we're not going to affect the reference in position 1 of the cats object. So that's great. Fairly easy to understand. There's a difference between creating a new reference to an object and creating a new object. This one can be dangerous if we're not sure why we're doing it. And you might think that's all there is to know about this, but like a bad musical, it keeps going on. If we have a list object or another mutable collection that refers to other mutable collections, then we really can get ourselves in trouble. So we know why we want to be careful using an assignment operator. If we want to be able to create a name that refers to a separate object but identical to this structure, we wouldn't just say figures equals shapes, because we know that would just create a name that points to the same object. So we think, okay, I know about that. I'm going to say figures equals shapes and then use that slice operator. Or maybe another method would be to say .copy. And that would be a better strategy. But let's see what happens now. Python is going to do exactly as you wish. It's going to take this list that Shapes was pointing to and make a copy of it. But what is a list? A list is just a collection of references. So the copy of this list object is going to look like this. Now we have two different list objects, and we could change one of them, but each one is pointing to other list objects. So if we make a change like this, let's call this circle A, B, and C, Shapes 2, which refers to this sublist, and then let's talk about position 1, which refers to this element in the sublist, equals C. So we're going to change this reference to the other circle. That's great, but we affected figures as well, because the number 2 position in figures is simply a reference to this list object. If we change this list object, it doesn't matter how we got there to change it, figures is going to be affected. And this might seem like a crazy example, but we use lists of lists all the time. So we need another tool. Instead of making a copy of the object that's pointed to by Shapes, we're going to make a deep copy. And in order to do this, we need to import the copy module. So at the top of our code, we'll say import copy. And then inside our code, we'll say figures equals copy.deepcopy Shapes. And what this deep copy function does is it goes deep into Shapes, as many levels as it needs to go, and recreates every single object that it finds. So we could have 5 levels of lists pointing to lists, no problem. It would take those final objects and recreate them. Notice I'm not recreating this third circle because it's not referred to anywhere in this hierarchy. But I do recreate all the shapes, and then I go up one level and I recreate all the lists. And with those new lists, I point them to the new shapes, but using the same structure as the original ones. And then I come up one more level and I create this sort of master list with references to the new list objects, but the same structure. And then finally, I bind this top level list to the name figures. Now there's no relationship between the structure that's referred to by the name shapes and the structure that's referred to by the name figures. If I want to change shapes at any level, I can do that without affecting figures at all. So I can remove this reference, change it to the third circle, and figures isn't touched at all. Let's explore that a little with some example code. So let's create a sort of deep list structure here. We'll make some strings. And then we'll create a couple of lists. The first one, deep list, is going to point to these 3 strings. And we'll create a top level list. We'll call it top list, of course. It's going to contain the list deep list and also the string mu. Remember, a list can contain different types of objects. And let's create 3 new references. We'll create top list 1 just as a reference to top list. We will create top list 2 as a copy of top list. And then we want to create a deep copy. In order to do that, we have to import the copy package. Top list 3 is going to be a deep copy. We're going to say copy.deepcopy top list. So right now, all 4 of these lists have somewhere in them a reference to meow. Let's take a minute to draw out what we've created. We created 3 strings, meow, woof, chirp. We gave them names, but the important thing is that we created a deep list that referred to the 3 strings. A list with 3 elements, each one referring to one of the strings. And then we created another list object with 2 elements. One of them pointed to this deep list object, and the other one just pointed to a string, mu. And then we named this object top list. And then we created a reference to top list that was called top list 1. This is just another name that points to the same object. And then we created a copy of top list. We copied this list here, but the list itself contains the same references. So in the first position, we have a reference to the deep list, and in the second position, we have a reference to the string mu. And we call this one top list 2. And then finally, we created top list 3 as a deep copy. And the deep copy makes sure there's absolutely nothing in common with the original list. It actually goes down and creates new objects, a brand new list to point to those objects, and a brand new top list, and calls it top list 3. Now the deep confusing truth is that these string objects are immutable. Now the deep disturbing truth is that the string mu is immutable. So Python may realize that it doesn't actually have to create another object of the string mu, but it can just point this back without any consequences. But for that, there's no impact to us. We can just think of this model. And if these are immutable objects like custom classes that we make or other lists or something like that, then Deepcopy definitely makes another copy. All right, let's go back to our code and let's explore the impact. Let's look first at top list and the string in the second position, mu. So if we change that, let's look at the impact on the other three lists. Remember that top list 1 is a reference to the same list that was referred to by top list. Top list 2 is a copy and top list 3 is a deep copy. If we run this code, we see that top list 1 as a reference was affected by the change to top list. The other two were not affected. Now let's go deeper and let's change string 1. So to get there, we're going to go through top list into deep list, and we're going to change the 0 position here. So we look at the 0 position of top list, and within that, go to the 0 position of deep list, which currently points to this string meow. We're going to change it to ba, and then look at the same position in the structure of each of the other lists. We'll run this code again, and this time we see that, of course, top list 1 was changed because it's just a reference to top list. There are two names that point to the same object. Top list 2 was changed as well, because remember, top list 2 was just a shallow copy of top list. It only copied the first level and still referred to the deep list object. So when we changed a reference in the deep list object, it affected not only top list, but also top list 2. Top list 3, on the other hand, deep copy went down as far as it needed to go to create a complete parallel structure with brand new objects. Importantly, it made a copy of the deep list object, which has the effect of decoupling it from top list. If you'll pardon the pun, this is deep stuff, and if you haven't seen this before, it's going to take a while to sink in. Draw some pictures and play around with some code of your own. Duplicate what I've done here, make sure you can get the same results, and then see if you can anticipate what other results will happen as you play around changing objects in these lists. It's critical to understand how these structures work in references and copies and deep copies, because if you don't, at some point it'll come back to bite you.